Hello, welcome to video 5 in the calculus section. Today I'm going to be discussing error estimates using partial derivatives. And so what we have here is we suppose that we have a function z of two variables, and similar comments could also apply if there were more than two variables, but we're just going to discuss the case of two variables. And z is what you're really interested in. But z is a function of two variables, x and y, that you measure. So you measure x and y, and then you calculate z based on some formula. And when you measure x and y in a real-world situation, of course, any measurement will be prone to some sort of error. And you may be able to estimate the size of the error. Say the error is no larger than some amount in your measurements. But then the question is, how large should you say the error is in z? If you calculate z from the measurements of x and y, which have some known errors. And so this is the question that we want to try to answer in this video. How should you report the error on z when z is calculated from some measured quantities? Okay, so we'll first think about this when z is only a function of one variable, x. And then we'll have a natural extension to the case when z is a function of two variables. And so suppose z only depends on x. And then we have this approximation. This is actually just a different version of the linear approximation I discussed in the previous video. If you divide through by delta z, the change in z due to a small change in x is the change in x times derivative of z with respect to x. In fact, when you take the limit as delta x goes to 0, this second equality here becomes exact, not just an approximation. And so this is the same linear approximation we discussed in the previous video. The small change in z is approximately the derivative of z with respect to x, or f prime of x, times the change in x. And so if we have, say, a small error in x, we can say delta x is that error. So say we measure x, and we know that the error about plus or minus delta x. Then we would report we would estimate the error on z based on this formula. So the error in z is approximately plus or minus the derivative of f with respect to x times the error in x. Or I'm taking absolute values since we don't know the sign of the error. We want to eliminate the plus or minus. The modulus of delta z, the error in z, is approximately the derivative of z with respect to x times the error in x. So this is the formula that we would use in order to figure out the error, or estimate the size of the error if z was calculated based on one measurement. And so I'm going to give a kind of explanation of why this is, another explanation based on this picture. And so we have, say, z is a function of x. So z is given by this function whose graph is shown by the red curve. Looks like the top half of a circle. And so if we measure x, we would then calculate z as shown. But then suppose there's some error in x. So we know x is actually within some interval with the half width delta x. Then, well, we'd estimate the size of the error in z by projecting that interval up, as shown, onto the tangent line to the graph, and then over onto the vertical axis to give the error in z. And this is exactly the formula. So the error in z would be there, where we just project up to the tangent line and then over, as shown. And this is this formula. So z is approximately the calculated value, f of x, plus this amount of error, delta z, and delta z is has modulus estimated by the derivative of f with respect to x times the error in x. So I'm going to do an example. Estimating the size of error when there's only one variable that you measure, and then you calculate z based on that measurement of one variable. And so the details are given here. Okay, and so we have z is calculated from x as 3x squared plus x cubed. And we measure x as 2 plus or minus 0.01. And so there's a potential for confusion here because I've written x equals this. I should maybe say x is approximately equal to this. There's some error here. We don't know what it is exactly. And I'm actually going to use the notation here. This part is x, the measured value, and this part is delta x, the error. They have some measured value plus or minus this error. And so we first of all calculate our estimate for what z is based on the measurement that we made. X is 2, and so we plug in x equal 2 here. 3 times 2 squared plus 2 cubed is 20. But then what should the size of the error be? So based on the formula from the previous slide, maybe I can go back. Okay, so based on this formula for the error, the delta z is going to be this derivative of the of z with respect to x times delta x. So modulus of delta z is approximately z dx times delta x. And here is z as a function of x. And so we calculate this derivative. 6x, the derivative of 3x squared plus 3x squared. That's dz dx. And then times delta x. So this is just an estimate of how large the error in z could be. And so this is, we'll plug in the value that we have for x. So we have here 12 plus 12 times delta x, which is 0.01. So we have 24 times 0.01, so this is 0.24. All right, and so this would be the size of error we would give for z, and then this is the calculated value. So we would write z equals 20 plus or minus this error 0.24. Okay, this is this example when there's only one variable. Z depends only on one variable, x. Now let's consider what happens when z depends on two variables. Okay, well, as you probably anticipate, rather than using the partial derivative, or sorry, the just derivative of f with respect to x, we use the partial derivatives of z with respect to the two variables. And so, and we use the same formula for the linear approximation that we discussed in the previous video. So we say z is a function of the two variables x and y. Z equals f of x and y. And the formula for the change in z, it was given us by a star in the previous video, is this one. So the change in z given by a change in x and change in y is this. And here we use the subscript notation for the partial derivatives. So recall fx is the partial derivative of f with respect to x, similarly for fy. And so this is what we'll use for the estimate of the size of the error. Now, of course, you don't know the sign, whether delta x is positive or negative, whether you overestimated or underestimated. And so in order to get a sort of most pessimistic estimate possible, we take the modulus of both the terms. Of course, it's possible these errors could cancel out, but we would take the modulus in case they add together because you don't know. And so the size of the error, delta z, is estimated by this formula. So I do want to add a disclaimer here. This is not the only way of treating error. In some cases, this formula for the approximation of the size of the error is a bit different. It's actually a different function of f, the derivative of f with respect to x times delta x, and the derivative of f with respect to y times delta y. But this formula is actually more pessimistic than other options. It gives a sort of worse estimate, and so you can use it to be safe. Other options give a slightly more optimistic estimate. But this is what we'll use here in the examples I'm going to show. And so I'm going to do some examples of estimating the size of the error when we have a function of two variables. And so the first example is shown here. It's similar to the example from the previous video with a tree that's modeled as a cylinder. Here we just say it's a cylinder. So we have a cylinder, and we measure the height and the radius with some errors, and we want to know what is the error in the volume that we would calculate. So, the same picture as before. Have this cylinder. Has some radius. It has some height. And the volume is a function of the radius and the height. So, as before, it's pi r squared times h. Pi times the radius squared times h. Okay, and so if we measure the radius and the height, this formula tells us what we should write as the volume. But if there's error in the radius and the height, we want to say what would be the error in the volume. So the error in the volume, delta v, be the modulus of the derivative of this formula for the volume with respect to r times the error r plus the derivative of volume with respect to h times the error in h. And this is, of course, similar to when we calculated that, or estimated the change in the volume using the linear approximation, but we've got the absolute values or modulus here because we don't know the signs of the errors. Okay, so the derivative of v with respect to r, partial derivative of v with respect to r, is 2 pi r h times delta r. Put in r. Derivative of v with respect to h is pi r squared h. Okay, so this is the formula then for v and for the error in v, delta v, and we just need to put in the numbers that are given in the example in order to answer the question, what is the uncertainty? What is the estimate of the error? So we have measurements of h as 2 plus or minus 0.1 meters. And so, once again, the h that we use in the calculations is the 2. That's what we've measured. And then the error, delta h, the 0.1. And the radius, 50 plus or minus 2 centimeters. And so we have to change the units in order to make them agree. So change it to meters. And so 0.5 plus or minus 0.02 meters. And this is 0.5 meters will be r, and 0.02 meters is going to be the error in r, delta r. Okay, so now we have everything that we need. We can calculate the volume and the error in the volume, or estimate estimate the error in the volume. So the volume is pi, r is 0.5 meters, and h 2 meters. And so if you put that in your calculator, you get this is two significant figures, or two decimal places I should say, 1.57 cubic meters. So if we just use the measurements and ignore the error, that's what we calculate for the volume. And then let's estimate the volume based on this formula. So size of the volume, size of the error in the volume, 2 times pi times r, 0.5 meters times h, 2 meters times the error in r, 0.02 meters, plus pi times r squared, 0.5 meters squared, times the error in h is 0.1 meters. Okay, so then put this in the calculator as well. 0.20, 2 decimal places, cubic meters. Okay, so this is the error in the volume. The volume we got was here, we calculated, and so we write that V is 1.57 plus or minus 0.20 cubic meters. So when we've estimated the size of the error in this calculated volume based on the measurements. Okay, so this is one example. I'm going to do one more sort of similar example. And so in this one, we're going to use the ideal gas law. So we assume we have a gas which is modeled as an ideal gas, and it'll 1 mole of the gas. We know the volume and temperature to some error. We've measured those with a given error, and then you want to calculate the pressure and say what is the error on that calculated value of the pressure. And so the formula that relates these things together is the ideal gas law. Is pressure equals the constant R times the temperature divided by the volume. Okay, and then the estimated size of the error in pressure when we calculate it from the temperature and the volume is going to be the derivative of the pressure with respect to temperature times the error in the temperature, measurement of the temperature, plus the derivative of pressure with respect to the volume times the error in the measurement of the volume. And so then we can take these two partial derivatives, derivative of p with respect to t and the derivative of p with respect to v. The derivative of p with respect to t is constant r divided by v. The error in t plus derivative of p with respect to v is negative r t over v squared times the error in the volume. Okay. Now, just to point out, since we take the modulus here, you can just assume everything is positive and get rid of this negative sign, and this is put a positive here because of the modulus. All right, and so these are all the formulas we need, and then you just need to put in the numbers in order to calculate the pressure and the error in the pressure. And so write down what is given in the example. The volume is measured at 0.1 plus or minus 10 to the negative 4th cubic meters. We use the cubic meters version in order to make the units work out so that we get pascals when we calculate the pressure. The temperature is 323 plus or minus 1 Kelvin. Once again, use Kelvin so that the units will work out to get pascals. And, well, we need to know what R is. R is a constant, and we know, given there, 8.314 joules per Kelvin. All right, and so we can put these in. So in order to calculate the pressure, we use the measured values. And so first of all, we have R is 8.314 joules per Kelvin. T, measured value, is 323 Kelvin. And V, measured value, is 0.1 cubic meter. And so approximation actually. So if you work out what that is, put it into the calculator, you get 26.85 kilopascals. Okay, and then, okay, so this is the calculated value of the pressure based on the measurements of the volume and temperature. And then we want to estimate the size of the pressure using this formula. And so the size for the air is approximately R divided by V, so that's 8.314 joules per Kelvin, divided by V is 0.1 cubic meters, parentheses there, times the air and the temperature, and the air and the temperature is 1 Kelvin. That's this term, plus another term right in here, the constant R, divide by V squared is 0.1 cubic meters squared times T 323 Kelvin times the air in the volume. Air in the volume was 10 to the negative 4th cubic meters. All right, and so calculate all that, and we get that this is 110 pascals. And so we've calculated the pressure, the air and the pressure, so we would write for the pressure this calculated value 26.85 kilopascals, and then this is pascals. If we want to convert it to kilopascals, we get plus or minus 0.11 kilopascals. Okay, so there's another example of using this estimate of the size of the air in a quantity that's calculated based on some measurements. So this is the end of this video. In the next video, we're going to go into another topic in calculus, integration. So we'll leave partial derivatives for the moment and move on to integration.